So that's like the main point from last time, from our last lecture, in part 1, about the finite element approach. So what we started with is basically putting the equation into a weak form. That's the first step of the finite element approach. Should you still remember what that equation is here on top? This thing here. What type of equation is it?
Diffusion.
Right. How do you recognize that?
There's no time?
Well, there can be a diffusion equation which is time dependent. No time means steady state, right? So it's a steady state diffusion equation. But what's the main part here in the equation? That's the second order spatial derivative. And then there is no, let's say, other derivative involved in this case. So if you think in terms of a full 3D space, second order is like taking the Laplacian of the field. And if you come from a different field, let's say if you think in terms of imaging and image filters, if you apply a Laplace filter to an image, what happens to the image is you smooth it out. That's exactly what's happening with the field here with U. We apply the Laplacian to U, our field. So the effect of it is kind of like it smooths out the field. And that's what diffusion looks like. Diffusion is like this smoothing out of a field. So whenever you see these spatial derivatives, second order in space, and no other derivatives in this case, that's a diffusion. So that leads to a diffusive field. If we then have a first order time derivative involved in the equation, then it's the non-steady state diffusion. That's the example we will come to in the homeworks, like the second homework about the finite element method. The first homework will be about this steady state diffusion equation. And then if you think of the wave equation, has also or can have this second order spatial derivative, but it combines it with the second order temporal derivative, if you remember when we look at the displacement formulation. And that gives us an oscillation, basically an oscillatory solution. So that's a wave then to propagate. So here diffusion equation, and then you see on the right side is the strong form. On the left side is the strong form. On the right side we have the weak form. And I put here the weak form that is basically the result when we add the boundary conditions. So we have on the left side the strong form together with particular boundaries. You see the boundary at 1 is a Dirichlet boundary, boundary at 0 is a Newman boundary. And when we consider these boundaries, we will find the weak form on the right side. So here then you have the term with h times w at 0. That comes from the boundary. And also we use these test functions for the weak form, w. And because of the Dirichlet boundary, it imposes that our test function at the Dirichlet boundary at point 1 is 0. That's now due to the boundaries. And so the boundary term at that boundary 1, that vanishes. So now we have the weak form which we need to solve with the finite element approach. Good. So next step is the function approximation. So now we approximate the test function and the solution field, solution function, with shape functions or with basis functions. And this is an approximation. So we approximate the function as an expansion on a certain basis. So it's not exact. And in particular for us, the shape functions that we want to look into are linear shape functions. So we approximate now like a smooth function with a piecewise linear basis. And so that's an approximation that we are doing. So we approximate this function in terms of shape functions. And now again, for our special example that we have with the boundary conditions, we have two conditions. One is that here n is now the number of elements. And sometimes when you open up a book and you look at the function approximation, n is the number of nodes. So for us, n is the number of elements because we have that Dirichlet boundary. And on the Dirichlet boundary, we don't have a degree of freedom anymore. We fixed what the solution field has to be on that boundary, which leads to that condition that NA at that boundary, the Dirichlet boundary, NA at 1 is 0. And that we add another n plus 1 shape function. So basically for the last node at 1, which imposes that shape function has to be 1. And that is due to our assumption that the solution field at 1 is Q and the test function at 1 vanishes, is 0. So that's now a particular case because of the boundary conditions that we impose. If we wouldn't have the Dirichlet boundary at 1, then we would just have n plus 1 shape functions. And we wouldn't need to impose that NA at 1 has to be 0. And we wouldn't need to have like a special case for n plus 1, that shape function. So you see in a very general case, often the function approximation just looks the same, just looks like that. You don't have this term here. And then they say that's the function approximation. You approximate it on a basis with NA, but then N is the number of nodes that you have, which is not the number of elements. So be aware of that difference. Because for us, each element has 2 nodes. So the last element, so in principle, we have n plus 1 nodes, but n elements. And because of the Dirichlet boundary, we then write the function approximation in this way. So we have this term, this additional term, which makes sure that we have the Dirichlet boundary imposed. That takes care of the boundary condition. Is that clear? So that's often a bit confusing. If you look up now literature, look into a book, you won't have something like that, for example. It's often just by introducing a general approach. And then at some point you impose the boundary conditions by looking at this function, at the nodal shape functions, and then you impose it on that node, for example. You fix then that degree of freedom. But so we write the function approximation this way, and then we can make sure that the Dirichlet boundary is considered correctly this way. And then you put this into the weak form, and out comes the linear system of equations. And again, I shuffled a bit around the expressions. But what you see basically is we have these integrals, these integral terms, which become KAB. And so you have the sum over B of KAB times DB. So it's like a matrix vector multiplication. So DB you can think of a vector, and these coefficients KAB as elements of a matrix, and then you have a matrix times a vector. That gives you the sum over B. And here you basically see only terms which depend on NA, plus our last shape function, the n+1 shape function. So these together, they make FA, one element in a vector again. So FA is again a vector. So if we put it into this matrix form, then we can write it as a matrix times vector equals a vector. KAB times DB equals to FA. What we are after are these DB coefficients, because then we know what the solution is, solution field. So in order to solve this, for DB, we just invert the matrix, stiffness matrix, and then write DB is the inverse of the stiffness matrix times the force vector. That's simple, as long as we can invert the stiffness matrix. So obviously the stiffness matrix has to be invertible to do that. Good. So that's where we stopped last time. This matrix form of the linear system of equations that we want to solve. So today what I want to continue with is first the choice of shape functions that we have. These NAs, NA functions. And then continue with a mapping where we start mapping then elements to a reference element. Good so far? Okay, so let's look at the choice of shape functions. Good, and for us, what we are interested in are linear basis functions. The finite element method is often using low order basis functions. So let's use a first order basis function, which is a linear function. So let's look at linear basis functions. And discretize our domain, which goes from 0 to 1, but could also be L if you want, and L being 1 in our case. and we discretize it with finite elements. So and what we are going to do now is basically, let's just start with one element, then two elements, and see how that would look like if we now set up our system of equation in our matrix form. So let's have a discretization. Oops. With a number of elements n equals to 1. How would that look like? Well, we have our domain, goes from 0 to 1, and we have one element, that's our element, and the element has two nodes, nodal points, at 0 and 1. So let's look at our function approximation. So W, if n is 1, only has one shape function, n1. So test function W of x has a single shape function, n1 of x. So we write W of x equals C1 times n1 of x. This is for x in our domain, so between 0 and 1. And we want W of 1 to be 0 in our example, which means that n1 of x has to be 0 at position 1. Let me just write instead of x position 1. So n1 of 1 is 0. That's our test function. Then for our solution function, solution u of x, look at our expression for the function approximation. So n is 1, so we have nb is equal n1, and plus the second term q times n plus 1, so that's the second shape function. So here we have u of x is equal to d1 times n1 of x plus q times n2 of x. Again for x between 0 and 1. And in this case, we impose that u1 has to be equal to q, which means that n2 at 1 is equal to 1. Oh, can you still see that, the boundary? Maybe let me put this a bit below it.
Professor, is it N2 of 1?
N2, you're right. Good catch, yes. And 2 at 1 has to be 1. And above we see that N1 at 1 has to be 0. So what kind of linear functions do we find now for N1 and N2 which satisfy these conditions? Both have to be linear functions. One has to vanish at point 1, the other has to be 1 at point 1. So what can we think of in terms of shape functions which are linear for these two? Well, we find linear shape functions N1 of x. What could that be?
One minus x.
1 minus x. Right, and 2 of x. What could that be?
X.
Right. So both are linear, and one is 0 at point 1, the other is 1 at point 1.
Why is that?
Say it again, Sisho.
Why we have these two equations?
Well, you have to impose that they are linear. So let's say NA of x has to be equal to a times x plus b. And now n1 at 1 has to be 0, and 2 at 1 has to be 1. So which means what are a and b? What are these a and b factors?
It's 1 and no, it's related to the a. If a equals 1, then a equals minus 1 and b equals 0. Yeah, b equals 1.
Right.
Oh, I forget that we assume that it's the linear function. Okay. Okay.
That's the options we have, basically. So that's how you find these shape functions. Good. So these shape functions satisfy these conditions, that they're linear and that they vanish at these points. So if you want, the sketch would look something like that. We have n1. Let's see. Oops. So a function like this for n1, which starts at point 1 and then goes to 0. And n2 would look like this. Starts at 0, goes to 1. That would be n2 of x. So these are our two shape functions. One element, two nodal points, two shape functions. And you have here how we approximate our functions with these two shape functions. Is it clear so far? So let's find the matrix. So let's look at our problem. So we had here the expressions for the matrix element KAB, the stiffness matrix, and for the force vector. So let's look at KAB. So what is A and B? They go from 1 to
1.
1 to n, so they can only be 1. So the only stiffness element that we have is K11, which is, let's look here. We had the integral from 0 to 1 of the derivative, then NA is N1, NB is also N1 times dx. So what is N1? So this means it's the integral of the derivative. Look at our function N1 is 1 minus x times the derivative of N1 again, dx. Oops. Sorry. So what is the derivative of N1?
-1.
Minus 1 times again minus 1. So integrated over 0 to 1, that gives us
Is that 1?
1. Yes. Good, so we have, that's the stiffness matrix already. What would be the force vector Fa? So A can only be 1, so we only have one entry. So we only have F1 is our, let me try and write that down, N1 times F. Then we have plus H times N1 at 0. Minus Q times the integral of the derivative of N1 times the derivative of N2. Is that clear?
Yes.
Good, let's put that in. So we have this first term. We can't do much about this one. So let's just write out what N1 is this 1 minus x times f of x dx. That's the first term. Second term, what is N1 at 0?
One.
Is 1, so it's just plus h. And then last term, see what is the derivative of N1? We had it above, it's minus 1. What is the derivative of N2?
1.
Is 1. Then we have the integral from 0 to 1. Gives us
-1.
minus 1, so it's plus q. So that's F1. Is this clear how we came up to that? Good. And now we have our system already in place. So in matrix form, we find that D1 is 1 over K11 times F1. That's the solution in this simple case. And let's come back to our function, to the solution basically. So u of x. So now we can write u of x is d1 n1 of x plus q times n2 of x, which becomes now this d1 factor, that's f1 over k1, k11. K11 is just 1, so it's basically just f1. So let's write that out again. F of x times dx plus h plus q. This would be d1 times n1. n1 is 1 minus x plus the second term q times n2. What is n2? n2 is just x. Good, and that's the solution for our problem. So if you look at the analytical solution, in the notes you see we have the analytical solution for this problem. So note that for if f of x is 0, we can neglect that integral term here. Compare that with the analytical solution. Well, you find it's exactly the same solution. So it's exact to the analytical solution. So note that for f of x equal to 0, and that term vanishes, this is the exact solution. So kind of like magic now. We went to the weak form, function approximation, linear system of equations, solved it with a linear basis, and what comes out is the exact solution actually, and we can neglect this fx term. And the only difference then comes in when f of x is not 0. Good, is that clear? Then we just, instead of use now one, we use 2 elements. So now let's choose a discretization with 2 elements. And the point that we want to come to is basically just see how it increases the degrees of freedom for our problem. So above you saw the only degree of freedom was D1. And so when we increase now the number of elements, this will also increase the degree of freedom. So let's choose a discretization with number of elements equal to elements n equals to 2. Let's do a little sketch again. Oops. It's hard to get a straight line on the iPad. Always bump over the boundary of the iPad. Good, so we want to have two elements. So let's choose the first element from 0 to 1/2. This will be element 1. And then element 2 from 1/2 to 1. So you see we have 3 nodal points that will give us 3 shape functions for 2 elements. So now let me quickly state that for our test function, so let's come back here to the function approximation. See, n is now 2. So for the test function w, we have 2 shape functions, n1 and n2. And for the solution field u of x, we will have this n plus 1, so the third shape function then. So let's write that down. So for test function w of x, we have 2 shape functions. So we can write w of x is equal c1 times n1 of x plus c2 times n2 of x. Again for x between 0 and 1. And with w of 1 equal to 0, that's what we impose to the test function. We see that now n1 of n1 at that point, at 1 has to be 0. And n2 at 1 also has to be 0. Good. For solution u of x, we find that u of x is now written as d1 n1 of x plus d2 n2 of x plus our Dirichlet boundary condition q times n3 of x. So this n3, that would be n plus 1 shape function. And here we impose u1 is equal to q, which means that n3 at 1 has to be 1. Okay, so what do we find in this case? So choosing linear shape functions. In this case, let me write it down to show you. So our first shape function, n1, will be 1 minus 2x for the range between 0 and 1/2. And it will be 0 from 1/2 to 1. So that would look like this. So this would be n1 of x goes from 1 at point 0 to 0 at point 1/2, and then continues being 0 from 1/2 to 1. And 2 of x. Now n2 x has 2 legs. The first one can be written as 2x between 0 and 1/2, and 2 times 1 minus x from 1/2 to 1. How would that look like? So this would be n2, sorry, x is 1 at 1/2 and 0 on the other two nodes. Good. Final shape function n3 of x. This will be 0 from 0 to 1/2. And we can write 2x minus 1 for 1/2 to 1 for that range. So in this case, what color do I have? So it's this one. Here the function would look like that, going to 1 at the last point. So that would be n3. They're all piecewise linear. So these are piecewise linear functions. And if you want, they can be called like shifted and scaled tent functions, like a tent. Especially if you look at n2, for example. You see when we would choose 3 elements, 4 elements, 5 elements, we would have like all these little tent functions. So what we can write basically as a general expression for these sort of basis functions. So in general, we can write this as nk of x is x minus xk minus 1 divided by xk minus xk minus 1 for x in this range from k minus 1 to xk. Then we have the second leg is k plus 1 minus x over k plus 1 minus xk. That's the second leg between xk and xk plus 1. And 0 elsewhere, or otherwise. So this is just a more general way of writing down these piecewise tent functions, where we would have, let's say, xk here. Well, let's make nodal points. This would be xk plus 1, this would be xk minus 1. And then this function would look like this, being 1 at xk and 0 on all the other nodes. So that's our tent function, basically. You can check with the 3 functions we have above that n1 and n3 just happen to be at the boundary, so there is no other leg. The only kind of real tent function is n2. So you can use, like for xk, you can use 1/2. Xk minus 1 is 0 and xk plus 1 is 1 for the example here above. So these nk, these are basically now basis functions, linear basis function that we can use. So 2 things to note here. First, note that for our solution, u, we have now 2 degrees of freedom, d1 and d2. These are the 2 unknowns now. So when we increase the number of elements, we increase the number of unknowns. Or the same, in other words, is we increase the degree of freedom. So let's quickly note that down. So 2 elements, that increases the degree of freedom. In this case, it's d1 and d2 now. Not just d1, like when we had 1 element. And the second one is when you look at these tent functions, you see they only have local support. They are only non-zero between xk minus 1 and xk plus 1. So it's a function with a local support. And that's different to, for example, if we choose the FFT method, there we basically have to have the points, the function value at all grid points. Here it means we only need to have the function values then at these few points where it's non-zero. Basically in this case it's only at point xk. So that means it has a local support and it becomes a local method, therefore. So basis functions nk of x have only local support. This becomes a local method. Like as compared to, for example, the pseudospectral method. pseudospectral method is a method with global support. So local methods have often the advantage it's easier to parallelize local methods, because at the end we only need to exchange a bit of information from one neighboring partition to the next when we split these up, where a pseudospectral method needs to exchange all the information to all other domains. So local methods are less intensive in terms of communication of information, and they only need to exchange information to the neighbors. Now also note that we just made the choice to have linear functions. That's a choice we can make. So we could also choose higher degree functions as basis functions. So we could choose higher order shape functions. For example, we could use polynomials, etc. And this would lead to a higher order finite element scheme then. Or which would lead, if you would choose so, which would lead to a higher order finite element scheme. So you saw with the finite differences, we choose lower order stencils or higher order stencils. And we looked at these stencil expressions, for example, with the finite difference approximation. With the finite element method, you would look at these basis functions, and the order of the basis function gives you then the order of the finite element method. In engineering, it's often a low order basis function that we would choose. A linear basis function, for example, is the most simple one. Or we could use quadratic basis functions, for example, to increase the order a bit of a finite element. When we come to then the spectral element method, our last method we come to, we will see that there we use usually higher order polynomials as basis functions. That makes the spectral element method a higher order method compared to the finite element, which basically by choice is often a low order scheme. Good. Now, let me quickly mention the homework for you at this point before we come to global and local views. So you saw we defined now the shape functions. So let's figure out what is the matrix form for this little example with two elements. And that's your homework, basically. Let's try and do that for next Thursday. So here, let me put down the homework for you. So derive the matrix form for n equals 2. So we want to have this explicitly figured out. And I give you this solution so that you can compare it by yourself at the end. So show that in this example with 2 elements, we have k11 is equal to 2, k12 is equal to k21 is equal to -2, and k22 becomes 4. And then we have the force vector F1. Here we have the integral from 0 to 1/2. 1 minus 2x times f of x dx plus h. And F2 becomes a bit longer expression, goes from 0 to 1/2 of x times f of x dx plus 2 now from 1/2 to 1 of 1 minus x f of x dx plus 2q. So write down like these expressions we put here. Make it very explicit. Write down what k11 is, k12, which is then becoming k21, and f1 and f2. And this should be then the solution you come to. So in this case, the system, the matrix form will look like this. This is our stiffness matrix, the 2 degrees of freedom, d1, d2, 2 coefficients, is equal then to these expressions for f1 and f2. So do that as a little homework with a piece of paper and a pencil. Just figure out why k11 is 2, why k12 becomes -2, etc. Is that okay? Good. So we have 10, 15 minutes more. So let's start with the mapping, global and local mapping. So in this example, you saw we just chose the elements such that they have the same length, 1/2. So each element is exactly the same length. But what would happen if we would change that and allow for some arbitrary length of the elements? Instead of having like a regular discretization, now choose something irregular. So then you see these shape functions, they will become all different. These nk functions would have all kind of different ranges where they would be defined. So how can we make this a bit more convenient? So question is, How about giving it a bit more flexibility?
Professor,
Yeah.
is it K224 or 2? Show that K11 is 2, K12 minus 2, K22 is 4 or 2?
Yes, it's 4.
Okay.
Let me quickly check. But should be 4, yes. And have kind of all arbitrary element sizes. Because we might want to adapt the element size to the geometry of the body. Make smaller elements where the geometry is complex, and choose larger elements where the geometry is very irregular. And this basically leads to the idea of a reference element to map the shape of each element to a reference element, where the reference element is always defined, say, between -1 and 1, where we have always the same shape function for that reference element. So let's see how that would look like. So the idea basically is to have a global versus local view. And let me come to the definitions of what we mean by global and local. So let us introduce the linear finite elements. In which the problem is solved. Then we separate between a global view, which is our physical domain, so corresponds to the physical domain, and a local view, which corresponds to a reference domain. So think of something where we have our domain goes from 0 to 1. That's our physical domain with some sort of function here. And now we're going to discretize it with a number of elements, but the element sizes, they can all vary a bit. We can have smaller elements here, it changes, then again, slightly bigger elements, etc. So that's how size of the elements all differ. So here, let's say this is XA, this is XA plus 1 for this particular element here. So this is our physical domain that we discretized. And now we're going to map each element to a reference element. So this one is like a mapping to a reference element, which, let's define, always goes from -1 to 1. That's our reference domain, or our reference element. So now it's a question basically of how that mapping looks like. How do we have to map each boundary XA and XA plus 1 to that reference domain -1 to 1? So let's see our global view. We can express that in terms of domains, which go from XA to XA plus 1, etc. Which has nodes at these physical coordinates, XA, XA plus 1, etc. Let's just focus now on this particular element, and has degrees of freedom. Associated to each node, so dA and dA plus 1. And now comes the main point. It has a shape function, or shape functions, which would be NA of X and NA plus 1 of X. Where NA of X now is defined as our piecewise linear functions, these tent functions. So it's going to be X minus XA minus 1 by, you see, we can write the element size, A minus 1, H is now the element size of element A minus 1, to XA plus 1 minus X over the element size of element H. So here this goes from XA minus 1 to X to XA. This goes from XA to XA plus 1. And 0 elsewhere. So if you want, this would be this little tent function. And 0 everywhere else. So this would be NA of X. So it has kind of these skewed legs now, depending on the element sizes. So here we just wrote HA or HA minus 1. So HA, there would be, for example, XA plus 1 minus XA, the element size. Good. So in the global view, all these shape functions NA are slightly different because this element sizes, they can vary. So they all have a slightly different range of where they are actually valid. If you want, we can also put down the shape functions for the first and last nodes. That's also in the global view. Well, let me just add this as a way to make the notation complete here. So the shape functions for first and last node. Then we have n1 of x. Just has then this one leg which goes from x1 to from 0 to x1. There's size h1. Yeah, and 0 else. And this last point, this n plus 1 shape function, that would go from xn to xn plus 1, which we can write this way for xn between for x between xn and xn plus 1, and again 0 else. So these would be these last legs here, this one and this one. That would be n1 x, and here we would have n plus 1 of x. This being x1, x2, etc. Good. So something to note here is that the stiffness matrix, these KAB elements, with these shape functions, the stiffness matrix becomes symmetric and banded. So it has local support, everything else becomes 0. So notice here the stiffness matrix. KAB, just K, it becomes symmetric. And a banded matrix, banded. For these shape functions. So K would look something like K11, K12. You have then K12 being symmetric, K22. Then you have K23, K33, and so on. everywhere else it would be 0. Here would all be 0. There's only this banded stiffness matrix. Good, so that would be the physical domain, how we discretize it. But you see, it becomes a bookkeeping issue with all these different NAs, all these different shape functions. So how can we make it a little bit easier to compute these entries for the stiffness matrix? K11, K12, etc. They all become then like different expressions because all the shape functions are slightly different. So that's the idea with the reference element. So the local view is this reference domain view. And here we can basically define a reference range from xi1 to xi2 and 2 shape functions, n1 and n2. So the local view has the domain from xi1 to xi2. And in practice, we can just choose -1 to 1, which is a good range. The nodes here, they are position xi1, xi2. It's always fixed. The degrees of freedom, we have our D1 and D2. And the shape functions are always N1 and N2. So the interpolation, the function approximation of U then becomes that U as a function of position xi is D1 N1 of xi plus D2 N2 of xi. So now it's very easy. This is always the same for the reference element. So what we need is now a mapping that maps position X to the corresponding position xi within the reference element. So that's our mapping, basically. If you want, that goes from X to xi. That's the mapping that we need. We can just say this is the mapping xi, basically, which maps the range from xa plus 1 to our reference xi1 to xi2 reference range. So the mapping is basically a function of X. What's xi of X, for example? Good, let me quickly finalize this. And then we can come back to it next week. So mapping. So we need a mapping between both views. Such that our mapping psi maps from the physical domain, the element, to our reference element. And we want to have that the mapping of point xa becomes position psi1, and the mapping of xa plus 1 becomes psi2. Good, so now we are again left with a choice about this mapping function. What should that mapping function be? And because of simplicity, we choose again a linear mapping function for that. So assuming a linear mapping, psi of x then is coefficient c1 plus c2 times x. So what we find for these coefficients, well, we find that psi of x now is 2x minus xa minus xa plus 1 divided by the element size HA. And we can go back to the physical domain. So given we have position psi, we then want also to go back to the physical domain x again, so that it's an invertible mapping. So x of psi then becomes 1/2 HA times psi plus xa plus xa plus 1. That maps it back into our element. Good, let's finish here. We're a little bit over time. But I hope you see where we're going basically with this. So once we have that mapping, which is a simple linear function that determines, given a position x, what's the position in the reference element. And now we're going to compute these stiffness terms within the reference element, because here the shape functions are always n1 and n2, always the same within this range. So we will see next week how we can just write this down basically in terms of the expressions. Then all the geometry, basically, if you want, all the different element sizes, they are accommodated by this mapping. So once we have this mapping, that takes care of the geometry in the physical domain. But then we can compute very easily what these stiffness contributions are, stiffness elements within the reference domain. Do you have some question to that? No? Yeah, let it settle a bit. And then we see why this becomes very convenient to do this sort of mapping. It looks like we're introducing an additional complexity to it, but this gives us then a way more convenient way of computing these terms for the stiffness matrix, for example. The goal is still the same. Find these matrix expressions, find the stiffness matrix, force term, vector, and then have this linear system of equation that we can solve. Good. So don't forget the homework. Let's do that for next Thursday when we meet again. So that's a little exercise to once write down what these expressions are. You see, for the homework, we don't need that mapping yet. We don't use it yet. Yeah, it's really just to basically find out, once we have the element set and once we have the shape function set, what are the matrix expressions. And then next time we continue now with the mapping. Good, let me stop sharing this one. So is it good with everyone? Needs a bit of theory to go through at the beginning. But then once we have that figured out, hopefully it's very easy then to attack the example, the homework example, when we code it up. So hopefully we can come to that and next week, next Thursday. We finish up with the mapping and how we put everything together in order to have these matrix forms. And then we can actually apply this to the little example about the steady state diffusion and code this up. Good? Good with everyone? Okay. Look at it, try and make the homework done by next week. And then we can continue with finite elements. Okay, good. Then let me wish you good weekend for us here. Good weekend for you and the long midterm break. It's 2 days, it's like not really a midterm break, but at least we take everything we can. 2 days is always good. Good. See you next Thursday.
See you. Thank
See you,
you.
Professor. Thank you.
Bye, everyone.